Hi, Stu Schwartz from MasterMathMentor.com. This is video BC26b. The topic is manipulation of series, and it covers the BC manual pages 128 through 130. In number 10, we are told that f of x is equal to 1 over 1 plus x. We are given four expressions that are similar to f of x, and we are asked to write them in terms of f. In A, we are given 1 over 1 plus 2x. The only thing that has changed is the x is now changed to 2x, so this is simply f of 2x. In B, we're given 1 over 1 plus x squared. The only thing that has changed is the x has changed to x squared, and therefore this is f of x squared. In C, we're given 4 over 1 minus x. There are two changes here. The x has changed to negative x, and we've multiplied our result by 4. So this will be 4f of negative x. In D, we have 4x over 1 plus 3x. There are two changes here. The x is changed to 3x, and we've multiplied our result by 4x. So this is simply 4x f of 3x. We now define f of x as 1 over 1 plus x, which we know is the Taylor series 1 minus x plus x squared minus x cubed plus x fourth minus dot 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 plus negative 1 to the n, x to the n plus dot dot dot. With that in mind, we again look at problem A above, and we call g of x 1 over 1 plus 2x. We said that this was equal to f of x, and by our definition of f of x, this will be 1 minus 2x plus 2x quantity squared minus 2x quantity to the third plus dot dot dot. So 1 over 1 plus 2x can be written as 1 minus 2x plus 4x squared minus 8x to the third plus dot 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 plus quantity negative 2x quantity to the n power plus dot dot dot. And problem B above, 1 over 1 plus x squared, we will let equal to g of x, which is simply f of x squared. And that will become, by definition, 1 minus x squared plus x to the fourth minus x to the sixth plus dot dot dot. So we can write our expression 1 over 1 plus x squared as 1 minus x squared plus x to the fourth minus x to the sixth plus dot 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 plus negative 1 to the n, x raised to the 2n plus dot dot dot. In 13 and 14, we will again use our useful series f of x is equal to 1 over 1 plus x, which expands to 1 minus x plus x squared minus x cubed plus x to the fourth minus dot 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 plus the quantity negative x quantity to the n power plus dot dot dot. We would like to write a power series for g of x equals 4x over 1 plus 3x. Comparing that to our f, we realize that the x downstairs has been replaced by 3x, and the entire expression has been multiplied by 4x. So we can write g of x, which is 4x over 1 plus 3x, as 4x f of 3x. And that will be 4x times the quantity 1 minus 3x plus quantity 3x quantity squared minus 3x quantity cubed plus dot dot dot. And when we multiply out, we get 4x minus 12x squared plus 36x cubed minus 108x to the fourth plus dot 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 plus 4 times negative 3 raised to the n, x raised to the n plus 1 plus dot dot dot. D reads g of x is equal to x squared over 1 minus x cubed. This looks complicated, but realize that there have been two changes made compared to f. We have replaced the x downstairs with a negative x raised to the third, and we have multiplied the entire expression by x squared. So we can write g of x equals x squared over 1 minus x cubed as x squared times f of negative x raised to the third. And therefore this is x squared times the quantity 1 plus x cubed plus x6 plus x ninth plus dot dot dot. And this turns out to be x squared plus x to the fifth plus x to the eighth plus x to the 11th plus dot 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 plus x raised to the 3n plus 2 plus dot dot dot. In a previous video, you were given that the inverse tangent of x could be written as its Taylor series, x minus x cubed over 3 plus x to the fifth over 5 minus x to the seventh over 7 plus dot dot dot. Generating this is easy enough. However, you will have to take successive derivatives. After the first derivative, we have to use the quotient rule, and it gets more and more involved. As you can see, every other term has a zero coefficient, so it will take a long time to establish a pattern. Let's try to do this in another way using a parent function. We will use a parent function of f of x equals 1 over 1 plus x, which we know is 1 minus x plus x squared minus x cubed plus x to the fourth minus dot dot dot. We then think of f of x squared, which will be 1 over 1 plus x squared, which is 1 minus x squared plus x fourth minus x to the sixth plus x to the eighth minus dot dot dot. Now we integrate that expression. The integral of 1 over 1 plus x squared dx is the inverse tangent of x, which is x minus x cubed over 3 plus x to the fifth over 5 minus x to the seventh over 7 plus dot 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 plus c. We know that the inverse tangent of 0 has to equal 0 plus c, which is equal to 0, meaning that c is equal to 0. So the inverse tangent of x is equal to x minus x cubed over 3 plus x to the fifth over 5 minus x to the seventh over 7 plus dot 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 plus negative 1 to the n raised times x to the 2n plus 1 divided by 2n plus 1 plus dot dot dot. Let's now get the interval of convergence. We use the ratio test and look at the limit as n approaches infinity of the absolute value of negative 1 x to the 2n plus 3 over 2n plus 3 times 2n plus 1 over x to the 2n plus 1. This is the limit as n approaches infinity of negative x squared, which has to equal a number less than 1, and therefore x is between negative 1 and 1. If x is negative 1, our series is negative 1 plus a third minus a fifth, which is an alternating series and converging. Similarly, if x is equal to 1, our series is 1 minus a third plus a fifth plus dot dot dot, and that's also alternating and converging. So the interval of convergence is the closed interval negative 1 to 1. If we look at the inverse tangent of 1, therefore, this becomes 1 minus a third plus a 1/5 plus dot dot dot, and we know that that's equal to pi over 4. So therefore, we can express pi as 4 minus 4 thirds plus 4 fifths minus 4 sevenths plus dot dot dot. Even though this series converges to pi, it converges very slowly. To get 1 decimal place accuracy, we need 19 terms. 2 decimal place accuracy, 199 terms. 3 decimal place accuracy, 2001 terms. 4 decimal place accuracy, 20,001 terms. And 10 decimal place accuracy needs 5 billion terms. This series was discovered by Gottfried Leibniz in the year 1676. There are many infinite series that, when expanded, will give some expression involving pi. For instance, pi squared over 6 can be written as summation n equals 1 to infinity of 1 over n squared, which is 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared plus dot dot dot. These are just but a few of them. Some of them are alternating series. However, most of them take many terms to converge to pi and are inefficient in finding them. The last one, pi over 2, is equal to summation n equals 0 to infinity of 2 raised to the n times n factorial squared divided by 2n plus 1 factorial converges very, very quickly. In number 16, we want to find the first 4 non-zero terms of e to the x cosine of x. We will do this by the conventional way. We can do this because successive derivatives do not get really difficult to take. So f of x is equal to e to the x cosine of x, and cosine of 0 is equal to 1. So f prime of x is equal to e to the x times the quantity cosine of x minus sine of x, and f prime of 0 is also equal to 1. F double prime of x is equal to negative 2 e to the x sine of x, and f double prime of 0 is equal to 0. F triple prime of x is negative 2 e to the x times the quantity cosine of x plus sine of x, and f triple prime of 0 is negative 2. And the fourth derivative of f at x is equal to negative 4 e to the x cosine of x, and the fourth derivative of f at 0 is negative 4. So e to the x cosine of x can be written as 1 plus x minus 2x cubed over 3 factorial minus 4x to the fourth over 4 factorial plus dot dot dot. Therefore, e to the x cosine of x is equal to 1 plus x minus x cubed over 3 minus x to the fourth over 6. We don't have nearly enough terms yet to establish a general term, but that has not been asked for. We can do this in another way. We write e to the x cosine of x is equal to the product, quantity 1 plus x squared over 2 factorial plus dot dot dot, times the quantity 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus dot dot dot. We are going to attempt to multiply these term by term, and we will go up to x to the fourth for each expression. So e to the x is 1 plus x squared over 2 plus x cubed over 6 plus x to the fourth over 24 plus dot dot dot. And cosine of x is 1 minus x squared over 2 plus x to the fourth over 24. And we write the terms in the proper columns. Like long multiplication, we will multiply each term on the bottom by each term on the top. We multiply the 1 by every term above it, and we get 1 plus x squared over 2 plus x cubed over 6 plus x to the fourth over 24. We then multiply the negative x squared over 2 by every term, and we get negative x squared over 2 minus x cubed over 2 minus x to the fourth over 4. We don't have to go any further because the largest term that we want is an x fourth term. Finally, we will multiply the x to the fourth over 24 by every term above, and we only have to do one multiplication, multiplying it by 1, because anything else will have a higher power. We just simply get x to the fourth over 24. Finally, we add our like terms, and we get 1 plus x minus x cubed over 3 minus x to the fourth over 6 plus dot dot dot, the same answer we got to the left. This method is not necessarily easier, but we will find that sometimes it is necessary if the doing it by the definition involves derivatives that get more and more complicated. In 17, we would like to find the 6th degree Taylor polynomial centered around x is equal to 0 for sine of x over 1 plus x. We will attempt this both ways. First, by using the definition of a Taylor polynomial, and secondly, using infinite series. We start by plugging in 0 into our expression, and we get f of 0 equals 0. We then take our derivative by the quotient rule. Squaring the bottom, we get 1 plus x quantity squared, and upstairs we get 1 plus x times cosine of x minus sine of x. Plugging in 0 into the derivative, we get 1. We then contemplate taking further derivatives, and we realize that this is going to get bad. We have to square the bottom, getting a 1 plus x quantity to the fourth. And upstairs, we're going to have the bottom times the derivative of the top, which is going to involve a product rule. And then the top times the derivative of the bottom, which is going to involve a chain rule. And we are faced with having to take 6 derivatives. It just isn't worth it. Sine of x over 1 plus x can be written as the series for 1 over 1 plus x times the series for sine of x. And we get the quantity 1 minus x plus x squared minus x cubed plus x to the fourth minus dot 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 times the quantity x minus x cubed over 3 factorial plus x to the fifth over 5 factorial minus dot dot dot. Since we want a 6th degree Taylor polynomial, the product of any two terms can have a maximum power of 6. Since the expression for sine of x only has odd powers of x, there are only 3 ways to get a power of 6. An x times an x to the fifth, an x cubed times an x cubed, or an x to the fifth times an x. So the 1 over 1 plus x needs at most an x to the fifth, and sine of x needs at most an x to the fifth. So we will be multiplying the expressions, the quantity 1 minus x plus x squared minus x cubed plus x to the fourth minus dot 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 times the quantity x minus x cubed over 3 factorial plus x to the fifth over 5 factorial minus dot dot dot. We first multiply our x of the sine of x expression by every term in the 1 over 1 plus x expression and get x minus x squared plus x cubed minus x to the fourth plus x to the fifth minus x to the sixth plus dot dot dot. We then multiply our negative x cubed over 6 by every expression in the 1 over 1 plus x that is less than or equal to a power of 3. And we get negative x cubed over 6, a positive x to the fourth over 6, a negative x to the fifth over 6, and an x to the sixth over 6. And then finally, we multiply our x to the fifth over 120 times every expression that will give a power of 6 or less. And that gives us x to the fifth over 120 minus x to the sixth over 120. Since everything is in their proper columns, we simply add up and we get x minus x squared plus 5x to the third over 6 minus 5x to the fourth over 6 plus 101x to the fifth over 120 minus 101x to the sixth over 120 plus dot, dot, dot. Coming up with a general term would be very difficult at this point. It seems that the numerators and denominators are the same for the first two terms, then the next two terms, and then the next two terms. Whether that would be true as we extend the expression out, we would need many more terms in the multiplication, or we'd have to bite the bullet and actually take our derivatives. A very important curve in statistics is called the Gaussian distribution curve, which is known to be the bell-shaped curve defined by e to the negative x squared, as shown. In statistics, it is important to find the area under the curve between any two x values. This means, of course, we need to integrate the expression. But it is impossible to find an expression that represents an antiderivative of e to the negative x squared. So we will use approximation techniques. We would like to find the integral from negative infinity to infinity of e to the negative x squared dx. Since very little area is added to the right of x equals 2 or to the left of x equals negative 2, we will settle for an approximation for the integral from negative 2 to 2 of e to the negative x squared dx. We will first approximate the integral from negative 2 to 2 of e to the negative x squared dx with 8 trapezoids. Realizing that our curve is symmetric to the y-axis, we can simply approximate the area from 0 to 2 of e to the negative x squared dx and double it, and we can use 4 trapezoids. So this area would be approximated by 2 times 1/2 the base, where the base is 1/2, times e to the 0, which is 1, plus 2 over e to the 1/4, plus 2 over e, plus 2 over e to the 9/4, plus 1 over e to the 4th. Doing the math, we find that the approximate area is 1.7612372268. Let us now do our approximation using series. We start with e to the x, which is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus dot, dot, dot. So e to the negative x squared will be 1 minus x squared plus x to the 4th over 2 factorial minus x to the 6th over 3 factorial plus x to the 8th over 4 factorial plus dot, dot, dot. So when we want to integrate 2, integral from 0 to 2 of e to the negative x squared dx, this will equal 2x minus 2x cubed over 3 plus 2x to the 5th over 5 times 2 factorial, minus 2x to the 7th over 7 times 3 factorial, plus 2x to the 9th over 9 times 4 factorial, plus dot, 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 evaluated from 0 to 2. And our general term will be x to the 2n plus 2 over 2n plus 1 quantity times n factorial. So how many terms of this series is necessary to have accuracy to 1 decimal place? We know that the error of an alternating series of n terms is the n plus first term. So the first term evaluated x is equal to 2, that is less than 0.1, is the 11th term. where n is equal to 10 because we start at 0, and that will give 2 to the 22nd over 21 times 10 factorial, which is 0.055. Even though it is impossible to integrate e to the negative x squared dx, the improper integral from negative infinity to infinity of e to the negative x squared dx is exactly the square root of pi. If and when you get to advanced calculus, you will prove this fact. We are shown the graph of f of x is equal to the square root of x times sine of x, and we'd like to find the area of the shaded region. It is very difficult to integrate this expression, so we will use a power series with 3 terms to approximate the area. We'd also like to find the error associated with that answer. We first need to find where the graph crosses the x-axis, so we set the square root of x times sine x equals 0. We get x is equal to 0 and pi. We can then write our expression as the square root of x times the quantity x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus dot dot dot. Therefore, y is equal to x to the 3 halves minus x to the 7 halves over 3 factorial plus x to the 11 halves over 5 factorial minus dot dot dot. So the area is simply the integral from 0 to pi of x to the 3 halves minus x to the 7 halves over 3 factorial plus x to the 11 halves over 5 factorial minus dot 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 dx. Integrating, we get the area is 2x to the 5 halves over 5 minus 2x to the 9 halves over 9 times 3 factorial plus 2x raised to the 13 halves over 13 times 5 factorial minus dot dot dot, evaluating from 0 to pi. And therefore our approximation is 2 pi times 5 raised to the 5 halves over 5 minus 2 pi raised to the 9 halves over 54 plus 2 pi raised to the 13 halves over 1,560, and that gives 2.787. This is an alternating series whose terms are getting smaller, so the error is the absolute value of negative 2 pi raised to the 17 halves over 17 times 7 factorial, which is 0.393. That amounts to a 14% error, and that's fairly substantial. The problem with this method is that although these do converge using series, they can slowly converge, so you need a great number of terms. We would need at least 3 more terms before our error would be less than 0.01. We finished this course with an analysis of the expression e raised to the I pi power, where I is an imaginary number. In the next slide, we will look at what this means geometrically, but for now, let's see what the algebraic value of this expression is. We start with the series e to the x, which we know is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus dot 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 plus x to the n over n factorial plus dot dot dot. Therefore, e raised to the ix power should be 1 plus ix plus quantity ix, quantity squared over 2 factorial, plus ix quantity cubed over 3 factorial, plus ix raised to the 4th over 4 factorial, plus dot dot dot, plus ix quantity to the nth power over n factorial, plus dot dot dot. Now recall that I squared is the square root of -1 times the square root of -1, which is -1. I cubed is I squared times I, which is negative I, and I to the fourth is I squared squared, which is negative 1 squared, which is 1. So e to the ix will equal 1 plus ix minus x squared over 2 factorial minus ix cubed over 3 factorial plus x to the fourth over 4 factorial plus ix to the fifth over 5 factorial minus x to the sixth over 6 factorial minus ix to the seventh over 7 factorial plus x to the eighth over 8 factorial plus dot dot dot. So we can now write this e to the ix, and we can divide the terms up and write this as 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the sixth over 6 factorial plus x to the eighth over 8 factorial plus dot dot dot. And then plus ix minus ix cubed over 3 factorial plus ix to the fifth over 5 factorial minus ix to the seventh over 7 factorial plus dot dot dot. We can then factor out in the last set of terms the I and write this as e to the ix is equal to 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the sixth over 6 factorial plus x to the eighth over 8 factorial plus dot 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 plus I times the quantity x minus x cubed over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial plus dot dot dot. And we now recognize those series. So e to the ix is equal to cosine of x plus I sine of x. And now if we let x equal pi, e to the I pi must equal cosine pi plus I sine pi, which is negative 1 plus 0 equals negative 1. So e to the I pi has to equal negative 1, or e to the I pi plus 1 is equal to 0. This relationship is called Euler's formula, discovered by Leonhard Euler in the year 1740, and it is considered to be the most beautiful mathematical relationship ever found, as it relates the 5 most important numbers in math. 0, the additive identity, 1, the multiplicative identity, pi, the ratio of a circle's circumference to its diameter, e, also found by Euler, and represents the limit as x approaches infinity of 1 plus 1 over x raised to the x, and is the number used involving exponential growth or decay, and I, the imaginary number. The question is, what does this remarkable formula really mean? How can we raise e to an imaginary power? Is there some geometric explanation that interprets this formula? We start with a unit circle on the complex plane, where the x-axis is the real axis and the y-axis is the imaginary axis. We will show 4 points on the axis: 1, 0, 0, I, negative 1, 0, and 0, negative I. If we start with the number 1, which is 1 plus 0i, exponential growth in the real plane means that this number 1 is continuously growing by the same rate. When that rate is positive, that number gets bigger and bigger, as we've seen. Imaginary exponential growth is different. It will move a point on the unit circle at a 90-degree angle. It's like the thrusters on a big ship. It doesn't move the ship forward or backwards. It just simply rotates it. So taking any number and multiplying it by I does not change its magnitude, just changes the direction in which it points. So we start at the point 1, 0, which means 1 plus 0i. Multiplying that number by e raised to the I theta has the effect of rotating that point theta radians in the counterclockwise direction. So multiplying 1 by e pi rotates the point pi radians, or 180 degrees counterclockwise. That means that we rotate to the point -1, 0, or -1 plus 0i, or simply -1. So there's your geometric proof that e to the I pi is -1. So in problems 21 through 24, use the geometric argument to determine the values of these expressions. In the homework, we will use our series to verify these answers. So 21 e to the I pi over 2 takes the point 1 and rotates it pi over 2 radians, or 90 degrees counterclockwise, getting to the point 0 plus I, or simply I. 22 e to the 3i pi over 2 will take the point 1 and rotate it 270 degrees, or 3 pi over 2 radians. And we get the point 0, -i, which is 0 minus I, or simply -i. 23, 2i e to the I pi is simply taking e to the I pi, which we know is -1, and multiplying that by 2i to get -2i. And 24, 4e to the I pi over 4 takes our point 1 and rotates it 45 degrees. And when we multiply that by 4, we get 2 times the square root of 2 plus 2i square root of 2. That's it for the BC course. There are other videos in the series covering the non-essential areas of BC calculus, and while these are not explicitly covered on the AP exam, they will enhance your knowledge. There is a huge amount of review material on the MasterMathMentor.com website specifically for the BC exam, and most of it is free. The solutions, if you choose to buy them, are not expensive and demonstrate not just the answers, but how to go about solving the problems. I hope you have benefited from these videos and they enhanced your learning if you use them during the dark days of COVID-19. If you take multivariable calculus in college or in high school, if your school offers it, there is material on this website as well. And also there is material for AP statistics. Best of luck to you all in your future endeavors.